Hello and welcome to my little flipped learning video on humidity and lapse rates for A-level weather and climate course. It's basically to help you understand the differences in stability in your syllabus. Stability leading to high pressure anticyclonic conditions basically, whereas instability denotes low pressure and therefore depressions and rainfall. First, let's have a look at humidity. What is humidity? It's the amount of water vapour in the air, and it's measured using a hygrometer, you may remember. There's water vapour all around you in the air now, and that is called humidity. There are three ways in which we measure humidity. As you can see, there's absolute humidity, which is the quantity of water vapour in a given volume of air, and we measure it in grams per cubic metre. There's specific humidity, that's a ratio of mass quantities of water vapour to dry air, such as that ratio. By far the most important, and the one you hear on the news all the time, is relative humidity, and we express that as a percentage, and we do that obviously because it's the most easily perceived type of humidity. It's very hard to really understand what you can't see, so probably the most useful way of expressing it is that, a percentage, and we can all understand therefore how much water vapour is in the air as a percentage. How do the percentages work? Well, there's this little activity which I'll probably do for you, but you can probably do quite easily. Saturated air is obviously 100% a relative humidity, whereas moist is more like 80 to 99%, and dry is 50% or less. I'm doing this on a quite cool anticyclonic day, and I can tell you it's 44% today. Whereas tomorrow, where it seems it's going to be raining, I've checked and it's going to be apparently about 84% relative humidity tomorrow. So even in a country like ours, we can get very high humidities. It's not just the jungle or at the equator that you might think. Okay, the first of a few graphs, but let's not panic yet. Let's have a quick look at what it's showing. We've got air temperature along the bottom, and we've got water vapour in grams per cubic metre up the side. So what measure of humidity is this graph showing? I hope you would know that the answer is absolute. I can't write with this thing. What is happening along this line here? Hopefully you can see along this line you've basically got air temperature cooling, and then we can see that basically that is the saturation point, which basically means to me and you that it is condensing from water vapour back into water droplets, and therefore that equals clouds to me and you, and eventually rainfall, of course. So all along this line is cloud formation. So at 10 degrees Celsius, you would get water vapour. How much it can hold is at 9.4. So you can see a quite clear relationship that with increasing temperature, the amount of water vapour that the air can hold increases also, and almost exponentially, I think you'll agree. So at 30 degrees Celsius, you have 30 degrees Celsius, you can see that it can hold 30.04 grams per cubic metre of water vapour. So a clearly strong relationship between you increase the air temperature, and therefore it can hold more water vapour. How can we get this X here? It says state two ways in which the unsaturated particle of air X could be water saturation. Hopefully you would guess that the answer is you can either bring it down that way or you can take it up that way. And what I mean by that is you decrease the temperature or you increase the water vapour content or the humidity of it to bring it to saturation point. We call this whole idea the dew point, the saturation point. Just like you find dew on the grass in the mornings, that's literally what's happened. Is at night time the ground has cooled the air above it and caused condensation to happen. So that lovely sparkling water shining upon the grass, and we call it dew. And you get your trainers wet if you go jogging in the morning. Is formed from dew point, so it's nice and easy to remember. The given parts of humid air must be cooled at constant pressure. This is this lapse rate that I'm going to talk about, and a relative humidity of 100% indicates the dew point is equal to the current temperature. So that's what that graph was showing us. All along that line you've got a humidity of 100%, and therefore dew point, and therefore condensation, saturation. Okay, there are actually four ways in which we can bring about saturation point. You can bring the water vapor to condense to dew point. We've got adiabatic or convective cooling, which is the one that we've been studying, which is basically as air rises it cools and therefore contracts and condenses. There's also orographic cooling and frontal uplift, which is you might guess spot from the other two types of rainfall, where either it gets forced over a mountain or it gets forced over an invisible mountain of cold air, and that's therefore forced to rise and cool, as we know. There's also advection cooling and radiation cooling that we've looked at with fog formation. If you remember, advection cooling is where it comes horizontally from off the sea surface to the land surface, and radiation cooling gives us radiation fog, where the land is really cold at night and cools the air directly above it, and you get fog and cloud formation that way. So 4 different ways of bringing water vapor to dew point or saturation point. Of these 4, the most effective at cooling are orographic and adiabatic, and basically because they're going upwards. So the most efficient way of cooling air is to send it upwards because of the environmental lapse rate is helping it to cool. We know that things get cooler the higher they go. The other 2 are less effective, advection and radiation fog, because they're only really horizontal movements of air or very close to the ground. So orographic and adiabatic are the ones that we're really interested in when we're talking about cooling to saturation point in the rest of this presentation. So we've gone from looking at humidity and what that is to now bringing in the idea of the lapse rate. We talked about lapse rates before. The environmental lapse rate, or the ELR, as you see it in books, is basically how quickly the air cools the higher you go, and we know that it's basically about 6.5 degrees for every 1,000 meters that you go up. The horrible bit now is I'm going to tell you that's not always true. It actually changes because of different factors. Height, for example. So the lower, nearer to the ground it is, I hope you would know that it would therefore cool slower because of the effect of the ground, and it's colder the higher you get. So it's not actually uniform throughout the troposphere. The nearer the ground you are, the lower the environmental lapse rate, i.e. it cools slower. Time of year, of course, if it's a winter or a rainy season, it would also be lower. Different surfaces, continental areas, it would also be lower. All those different variables, which I won't go into in detail now, but I'm just trying to get you the idea that it's not a constant. So let's bring in this idea of the adiabatic lapse rate. This says here, it's used to explain what occurs as a parcel of air rises, decrease in pressure and temperature, but increases in volume. So it's what we've said about cloud formation in general, is that to get a cloud, you need warm rising air, which is expanding and therefore taking up more volume in the air, and therefore it's less dense, and therefore it rises. We use this phrase adiabatic because it means internal change. So we're talking about the changes within, and I'm going to use this phrase a lot, a parcel of air. So it's a piece of air relative to a piece of air around it. So we're talking about air and differences in volume and therefore differences in density. And again, this is probably the difficult thing is trying to visualize those differences. Okay, there are actually 2 sorts of adiabatic lapse rates. There's the dry and the saturated adiabatic lapse rate. And all that basically means is cool dry air, which is your dry adiabatic lapse rate, and your more warmer water vapor rich or even saturated adiabatic lapse rate, which is the SALR as opposed to the DALR. You can see them there and there. So if you've got a parcel of air that's cooling and we don't get to condensation, so we don't reach the dew point, it cools at approximately 1 degree per 100 meters, you can see, which is higher or quicker than our normal environmental lapse rate. I hope you've spotted. So if you've got particularly dry air, it will actually cool quicker than our average environmental lapse rates. You can already see now that the environmental lapse rate varies because of how much water vapor there is in the air. The saturated adiabatic lapse rate, the key thing to think about is that it's actually slower than the dry adiabatic lapse rate, and the reason for that is is all to do with latent heat, and there it is. It's basically because as the air rises, it's releasing the latent heat that it took in from when it turned into water vapor. So think back to when this water vapor was water and it was evaporated off a surface. When it was evaporated, latent heat is the amount of energy required to change a substance from one state to another. So when it evaporated into water vapor, it took literally warmth from the surrounding atmosphere, heat from the atmosphere, and locked it into itself, if you like, and that remains latent within it. And then when it changes the state back again from water vapor to water droplets, it releases that heat that it's stored, and so it aids itself. So the key to understanding this is that it really sort of fuels itself as it cools. So it cools at a much slower rate than the dry rate, because as it's releasing its heat, as it's cooling, and coming into saturation, it's actually producing its own heat from approaching dew point. So let's have a look at this in graphical format, which is what A-Level likes to do. On the left, we've just got environmental lapse rates, and you can see that they're at different rates because of different air masses, and I won't go into that in any more detail than that. It's just showing that the environmental lapse rate is not constant, it changes with different conditions. The adiabatic lapse rate, what we're interested in, as you can see at the bottom, the DALR temperature, it decreases at about 10 degrees per 1,000 meters, so it's happily decreasing and decreasing as dry air. But once we get to a height of about 500 meters, you can see that the water vapor it was holding, because it's become so cold now, it's beginning to condense, and it's reached dew point. And as it reaches dew point, because it's now releasing its latent heat, it is warming itself quicker than if it was dry air, so it actually starts to cool slower and therefore goes up on this line, whereas if it was dry, it would just carry on going along this line. So when you start to form clouds, it gives it what we call instability, which means it gives itself another injection of heat, if you like, and so it rises quicker than it would like to. This red line, the dry adiabatic rate, would mean that it would cool and keep cooling and start sinking, but because it's reached condensation level, this air will now keep rising and form more cloud formation, because it's less dense than the surrounding air because of its latent heat that's being released. So hopefully here's a slide reiterating what I hope I've just explained. So you can see the relationship between ELR and both the environmental lapse rate, the dry adiabatic lapse rate, and the saturated adiabatic lapse rate influences the temperature and thus the density and buoyancy of a vertically displaced parcel of air in comparison with its atmospheric surroundings. It thus determines the character of air stability. So that's the key to all this. So what is air stability? It's an important concept. It determines the buoyancy of the air and thus development of cloud and fog. Cumulonimbus clouds or cumulus clouds are characteristic of unstable air. So like we've just been seeing on the graph before, unstable air is drying at the saturated adiabatic lapse rate and therefore rising and cooling, rising quicker because it's cooling less quickly than if it was dry. So it's the condensation back into water vapor that's aiding it in its rising because of the release of latent heat. So again, another slide reiterating what I hope I've said. So with stable air, you can see, look, a parcel of air displaced vertically upwards or downwards in the atmosphere will tend to return to its original position because the environmental lapse rate is less than the DLR or the SALR. Whereas the unstable air occurs when you've got vertically placed warm air parcel, blah blah blah, and that's when we get clouds, and that's because the ELR, the environmental lapse rate, is greater than both of those, the dry adiabatic lapse rate or the saturated adiabatic lapse rate, which means that both of these are cooling slower than the environmental lapse rate, so everything's rising and therefore giving us an instability and therefore cloud formation. So some lovely graphs again. Here on the left we can see that the environmental lapse rate is less than both the dry or saturated adiabatic lapse rate. So here we can see the environmental lapse rate is 6 degrees per 1,000 meters, and it's the green line. Here we've got the dry adiabatic lap rate, and it doesn't reach saturation point in this, so there is no saturated on here. But you can see that it's basically cooling faster, and so ends up cooler at 1,000 meters than the environmental lapse rate, and therefore this air will sink. And if it sinks, and it says which weather systems are associated, so if that's sinking air, of course, then that will give us anticyclonic conditions. Crikey, I can't write. Anticyclonic conditions, and therefore a high pressure system. Whereas in this case, you see the ELR is greater. So let's find the ELR again. In this example here, there's the ELR. So you can see it's 9 degrees. By the time it gets to 1,000 meters, it's cooled from 20 to 9 degrees. Whereas we can see the DLLR, the dry, which would go all the way down to 10.2 degrees Celsius, so it would still be warmer than the environmental lapse rate, the normal lapse rate, if you like. Whereas in this particular instance, as it gets to 500 meters, because it's so cold now, and because of the humidity that we've got in this air, it actually reaches dew point at that point, and so thereafter will not cool at the dry adiabatic lapse rate, but will cool at the saturated adiabatic lapse rate. And of course, because it's now releasing its latent heat and producing clouds, it will slow down in its cooling rate and will still be 12.6 degrees Celsius by the time it gets to 1,000 meters, and therefore be very unstable air. So it's almost 3.6 degrees Celsius warmer than the surrounding air if it's going at the environmental lapse rate. And you can see therefore how buoyant and less dense it is, and therefore it will rise and it will give us a low pressure system or a depression, of course. And you can see lovely big cumulonimbus clouds there. And that's the basics of it, and the most important ones. The last one through at the end is a thing called a conditional instability, where some condition has forced the stability to change from stable to unstable or vice versa. The key is, you can see at the bottom, it's when the air is forced to rise. Unfortunately, this is actually the most common scenario in this country, so it gets a little bit complicated. But I'll let you look at the graph in your own time. But basically, you've got to think about what's forcing the air to rise unnaturally quickly, and you've got to think about, well, what is the most common form of cloud and rainfall formation in this country? Is frontal rainfall. So basically what it's saying is the air is forced to rise over cold air, and therefore that affects the adiabatic lapse rates. And what's also forcing the air to rise is orographic or relief rainfall as well. So we get lots of depressions coming in, hitting lots of mountainous areas like Wales, so we get lots of conditional instabilities. It's forced to rise, and it becomes saturated, so that condensation occurs, and therefore, well, I'll leave you to read the rest of the graph. Hopefully it makes more sense to you now. A graph stroke diagram that I found on the internet, again, maybe to help you. We can see the environmental lapse rate here. Why is it such a squiggly line? That is basically telling you that the environmental lapse rate is not constant, as we've said before. You can see it's lower near ground level, and then it speeds up and changes throughout the atmosphere. Importantly, you can see the dry adiabatic lapse rate on that side is still cooling less quickly than the environmental lapse rate, and then when it reaches its dew point here, at the base of the clouds, and we get cloud formation, it then dries at the saturated adiabatic lapse rate, which is even slower, and therefore it ends up warmer than still the environmental lapse rate. But with cooling and increasing height, eventually the two meet, and that would be where the cloud top formation would cease. So that would be the top of your cumulonimbus clouds, if you like, which is why you can see clear tops to them. Eventually they do meet again, because it just gets cooler and cooler the higher you go. Well, so what? Why is all this important? Well, air stability is the key phrase in your syllabus, and so you need to understand what it means by stable and unstable, and why you get stable and unstable air. So this idea that it cools at different rates, the environmental lapse rate, the saturated adiabatic lapse rate versus the environmental lapse rate, all of these things combine to make air stable or unstable, more or less stable relatively, and that's what gives us these different, well, this is what explains the different weather systems. So you've learnt about high pressures and low pressures. This is how they're formed and why they're formed, and really it's the unstable air that's giving us these cloud formation, if we have to talk more about clouds, then the stratus or more layered clouds denote more stable air. Hey, thanks for watching.